Our next speaker is Professor Laurent Lessard. Laurent is an associate professor of mechanical and industrial engineering at Northeastern University in Boston. He received his bachelor's from the University of Toronto, his master's and PhD from Stanford. Before taking up his current position, he was a postdoc at London University and at Berkeley, and an assistant professor at the University of Wisconsin-Madison. His research interests include decentralized control, robust control, and optimization, for which he has received various awards, including the Hugo Stuck Best Paper Award. Today, he will give a talk on robust control perspectives in algorithm analysis and design. Please join me in welcoming our speaker, and sorry for the feedback loop.
All right. Well, thank you so much for having me. So my talk today is, I'm going to try to cover a lot of different topics. They all sort of center on this theme of viewing optimization algorithms as robust controllers and as dynamical systems more generally. So I want to start by just looking at a very simple problem of unconstrained optimization. And the idea here is that we're just trying to minimize some functions, and here D is usually a high-dimensional space. And we're looking for algorithms that are fast and simple, and we're going to look at first-order methods. So the idea is you have access to the gradient of the function, and the goal is to find the minimum of f. So very simple problem. And just to give you an idea of the sort of the setting and what this is going to look like, here I have contours of a quadratic function, and this is the minimum right here, the minimizer, and the goal is to find that point. So one thing you can do is something like gradient descent. It's the simplest algorithm you can think of. The idea is you start at a point, you move in the direction of the gradient, and you pick some step size. In this case, I'm calling it alpha. And you can see that if the contours of the function are really squished close together, then you can get this oscillating behavior, and you get generally really slow convergence. This plot over here is the error, so the distance to optimality, as a function of the number of iterations. So one common thing to do is to use some sort of accelerated method. What does this mean? Here's one example. This is called Polyak acceleration, also known as the heavy ball method. The idea is that you're going to take what looks like a gradient step, but you're going to add some extra term here called a momentum term, and you have to pick some new parameter beta, and that depends on the difference between your current and your previous iterate. So you're going to store one additional iterate, but the benefit is this can accelerate your convergence. Now, this alpha is not the same as the alpha from gradient descent. Actually, you can afford to take larger steps when you're using momentum, and what you end up with is faster convergence to the optimal point. But you can see you take bigger excursions on your way there, and you see this faster convergence reflected in the error plot as well. But that's not the only thing you can do. There's also this thing called Nesterov acceleration, and it's also called the fast gradient method. And the idea here is that you're taking what looks like a normal gradient step, but instead of evaluating the gradient at this point xk, you evaluate it at a point yk that is an interpolated point between your current and your previous iterate. So you don't evaluate the gradient where you are, you evaluate the gradient at some point between where you are and where you were. And then you use that to inform your next step. And if you do that, what you can see is you still get accelerated behavior, so you still get performance that's faster than gradient descent, but the effect of this acceleration, qualitatively is very different than what the heavy ball acceleration was doing. Here you seem to be taking shorter steps, but they're more direct. So the result is you still get there faster, but in a different kind of way. And as you might imagine, these two methods have very different behavior when it comes to how they respond to, let's say, if there was noise on the gradient, right? These step sizes are, in effect, amplifying the gradient. So if you added noise to the gradient, you'd be amplifying that noise, right? And so we'll talk about that a little bit later. And these alpha and beta are different from the alpha and beta here, and these all need to be tuned. And the point I'm trying to make here is that this idea of selecting an algorithm and also how to tune it is very much an art. And for the most part, you need to be a domain expert to figure out exactly how to tune these different algorithms and which ones to use when. So let me give you an example of how this can be an art. And I'm going to show you a simple example. We're just going to talk about gradient descent. We're going to think about, let's think about optimizing step sizes. We want to find the best possible step size. And let's say that we know that we have a smooth, strongly convex function. So it's twice differentiable, and we have a lower bound and an upper bound on the eigenvalues of the Hessian. And we just want to know, how should I pick the step size alpha to get to 0 as quickly as possible? So I can guarantee that I get to 0 as quickly as possible. And how fast can I actually get there? So there's a lot of different methods that people have proposed to solve this problem in the literature. And I'm going to show you two famous ones. So first is a bound derived by Nesterov in his textbook. So the first thing you have to do here is use cocursivity, which is a property of strongly convex functions, and you get this inequality. And then you do the following. So you take the distance to optimality at step t plus 1, and then you expand it using the formula for gradient descent. Then you expand the square, and you get this cross term in the middle. Then you apply that inequality, and then you get this thing over here. And then you use the fact that if you have a small step size over here, you can say that this whole term is going to be positive, and then you're left with this bound here. And you're like, okay, great. Well, this gives me a relationship between the next error and the previous error. Why don't I choose alpha in order to make this thing as small as possible? Seems reasonable. So if you do that, you get an alpha that's 2 over m plus l, and you get a rate that looks like this. This turns out to be the optimal rate for gradient descent. But this is not the only way to solve the problem. Polyak also had an approach. His approach is completely different. So he uses the mean value theorem to expand the Hessian. You can write that the gradient of f is equal to the gradient of f at optimality plus this piece here, which depends on the Hessian. And you can write this whole thing as some matrix a sub k times the distance to optimality. And then you use the fact that you have this relationship, and you can bound the distance to optimality, again, by applying the gradient rule, but this time you're using just a property of norms rather than using Cauchy-Schwarz or anything like that. And this time you get a different formula here that also relates these two things together. And again, you can find the alpha that minimizes this quantity. And when you do that, you get the exact same thing. Okay. Well, that's nice. It's convenient. And it is, again, the right answer. But it's weird that these formulas are actually different. And if you pick a different alpha, then these rate bounds are going to be actually different depending on which approach you used. They just happen to coincide when it's optimal, which is probably why these ended up in the book, right? They give the right answer. My point is that you have to be really clever to figure this out. And even if you are really clever, it's not clear that you're going to get the right answer or that you know you're going to get the right answer. Basically, you just have to combine various inequalities in a way that you think will work, and hopefully you get the right answer out of it, right? So the question is, can we turn this into more of a science? Can we figure out a more systematic way of solving these problems, finding the best possible bounds, being assured that they're the best possible, and not having to be so clever? So just an outline of the talk. The first thing I want to tell you about is that you can do this. And the idea is to view iterative algorithms as robust controllers. Not only that, we can analyze these algorithms, figure out these sort of best possible rates in a rapid and automatic way, where you don't have to care about the algorithm. You would use the same approach for every algorithm, and you would always get the best answer. And this involves solving small semi-definite programs that can be done really efficiently and that don't scale with the size of the problem. We can match or exceed state-of-the-art performance bounds. So the bounds that exist, we can either match them or improve them, and there is no case in which this doesn't happen. And finally, this way of doing tight analysis can lead to principled algorithm design. And I will show you some examples throughout the talk. So just to tell you what kind of results you can achieve for the same problem of optimizing gradient descent, this is what the result for gradient descent looks like. If you use step size alpha, gradient descent converges with rate rho if you can find me some positive constant lambda such that this matrix is positive semi-definite. It's a 3x3 matrix. So this describes geometrically a convex set. And it allows you to answer all sorts of questions, such as, if you fix the step size alpha, what is the best convergence rate that you can get? Or for a given convergence rate, what is the range of step sizes alpha that can achieve that? And of course, you can answer the original question as well. You know, what is the minimum convergence or the fastest convergence rate that you can achieve? And if you analyze this a little bit, you get this bound. If you eliminate lambda, which you can do with some algebra, you get that rho is greater than or equal to this, which is the same as what Polyak's bound found, and it yields exactly the same optimal value. Now, you might say, well, what am I supposed to do with this intuitively? I mean, what does that mean? It's just some matrix being positive semi-definite. Well, this particular one has a very intuitive interpretation, and this is the interpretation. You can rewrite that matrix inequality this way, and if you multiply both sides by the distance to optimality and the gradient at a time k, you get this expression. So distance to optimality time k plus 1 minus rho squared distance to optimality at time k, plus this piece here. And it turns out that this piece here is always non-negative whenever f is a strongly convex function. So what this tells you is that v of x, this function here, distance to optimality, is a Lyapunov function that proves that you converge with a rate rho. So this gives you an intuitive certificate that tells you how to interpret, that certifies the stability, the robust stability of the algorithm. So this is nice. This sort of framework is also called dissipation inequality, if you're familiar with that. Okay, so the outline of the talk is I want to show you how to write down iterative algorithms as dynamical systems. I'm going to expand on this Lyapunov approach to stability. The good news is that even for more complicated algorithms, the approach is very similar to what I just described. And you're going to get a certificate very similar to what I just showed you for gradient descent. And then, time permitting, I will show you some design examples for stochastic optimization and distributed optimization. So the good news is that Professor Ebenbauer already went through a lot of this material, so I can go through a little bit more quickly. But the dynamical systems interpretation, the idea is that if you have your dynamical systems equation here, so this is heavy ball method, you can write it as a feedback of a linear time invariant dynamical system with the gradient, static gradient operator. And the nice thing about this is that even though your x and your p is just your previous state and u is the gradient, these may be really high dimensional. Remember, usually you use gradient descent in millions of dimensions, and that's totally fine. So these identity matrices are really large, but you can see that these systems are diagonal. The linear part is diagonal. And each of the components of x and p evolve independently if you forget about the fact that they get coupled through this, right? So you can actually view this as a whole bunch of identical scalar systems that are acting independently on each component of y and u, and then this is the one troublesome part of the whole feedback loop that couples everything together. So this is the representation. You have some linear time invariant system, and then you have the gradient of some function, and then you have system matrices A, B, and C. And in this case, for gradient descent, this is what A, B, and C are. For heavy ball, this is what they are. And for Nesterov, this is what they are. So from this point of view, you can just plug and play different values of A, B, and C to analyze different algorithms in this framework. So as long as they have a representation like this, then the analysis is the same. What about the functions? Well, usually, functions are often defined, at least in optimization applications, in terms of the inequalities that they must satisfy. This is often the way that we write down classes of functions. We say, well, they're functions that satisfy the following inequality. And there are lots of examples. So convex functions, we write down inequalities that they satisfy all the time, right? Sometimes you can add more things. You can say, well, I also have Lipschitz gradients. Well, then there's a whole bunch more inequalities that you can write. And if you've taken a class on convex optimization, you've had plenty of fun with these sorts of inequalities. Or you can have strongly convex with Lipschitz gradients, and then the inequalities just get more and more complicated as you add more things that you know, right? But it's not just reserved for convex cases. You also have non-convex examples, and these have been studied throughout the literature when we want to study classes of functions that have some of the nice properties of convexity, but don't make as strong an assumption. And these are just some examples. The PL condition is a very well-known one. And you see all of these examples share something in common. They all have sort of quadratic constraints on x or on the gradient, and linear constraints on the function values. And this is sort of a recurring theme here. So the basic approach that I'm going to tell you about is that we take the algorithm and then we lift it into a higher dimensional representation. And in that higher dimensional representation, we can find very simple Lyapunov functions to prove stability. And by adjusting how much lifting you do, you can get less and less conservatism in your certificates. And that's the basic idea. Now, there are direct approaches that go from the algorithm directly to performance bound, such as the IQC approach, which I will mention a little bit later. But this is the approach I'm going to talk about today because it gives these nice interpretable certificates. Okay, so the basic idea is you start with an algorithm and its gradient, and this algorithm has some state x. And when you do the lifting, the idea is that you now imagine a lifted system whose state is your current x, and then the L previous inputs and outputs of your gradient. So you've lifted the state into this higher dimensional thing, and now you can write it as this lifted algorithm in feedback with repeated copies of the gradient. So this is still an optimization algorithm, but it's operating on a higher dimensional space. Now, why is that useful? It's useful because remember those inequalities that we had often couple pairs of points. Well, if you lift the state, now you have more pairs of points to use. And the more inequalities you can use, the less conservatism you'll have. If you only considered one iteration, then there isn't much you can't apply your inequality to very much. If you lift it to, let's say, 5 iterates, then you can compare the current iterate to the iterate 5 time steps ago, for example. That's the basic idea. And the outline of the approach is that we're going to look for a Lyapunov function that is quadratic in the lifted state and linear in the lifted function, so the function values at the k previous points. And then you write down all possible combinations of the valid inequalities satisfied by the function you care about. And you can generally write that in this form, where this is a linear combination of a whole bunch of inequalities parameterized by these positive parameters lambda. You could think of these as multipliers from robust control. It's the same idea. So if you know that a bunch of inequalities hold, then positive linear combinations of inequalities also hold, so you can write down in general an inequality of this form. And then you use the S procedure from controls. So you write down this inequality here, and then the goal is to pick a lambda such that you can show that this is true for all values of the state. And if you can do that, then because you know that these inequalities are always positive, then that ensures that this holds, and therefore you've proven convergence at the given rate. So it's very intuitive, and this is, a one-line proof that you have a convergence certificate. And if you increase the lifting dimension, then you have more variables here, more degrees of freedom, and then in general, you can get tighter certificates. So there's a lot of related work here, and I just want to touch on a little bit of it. The work that inspired some of our work here, it all started with this paper by Drury and Tabboul that first studied sort of the finite time performance of algorithms by saying, okay, well, if I know I'm only going to do n iterations, how can I guarantee that I have the best possible, or the worst possible worst case error after those n iterations? And they wrote that as a giant optimization problem. And this was refined by Taylor, Hendricks, and others in this thing called the Performance Estimation Program, or PEP approach. And this does give you tight bounds, but the optimization problem you have to solve to find those bounds scales with the size of the horizon that you want to analyze. Then there was works that looked at asymptotic performance. So there was the IQC approach, which was a paper by myself, Ben Recht, and Andy Packard. And I think we were the first to sort of look at what happens when you apply IQCs to this framework to try to characterize asymptotic performance. And then there was some follow-up work as well that further refined this idea and sort of looked at how different ways to do synthesis as well. The approach that I'm going to talk about today is similar in spirit to the PEP approach because it's a time domain approach fundamentally, and it recovers the same bounds as the IQC approach. So it's no more conservative than that approach. And in fact, you can show that the IQC approach with Zames-Falb multipliers, for example, is a special case of the Lyapunov approach, although those extra degrees of freedom apparently don't really bias anything, it seems. We get the same worst case rates. How efficient is it to use this kind of approach? Well, searching for Lyapunov function is solving a linear matrix inequality. It's a convex optimization program. The size, as I mentioned, does not depend on the dimension d. So if you're applying gradient descent to millions of dimensions, the only thing that matters is how many time steps of memory your algorithm has. So you're not going to have to solve a million by million linear matrix inequality, thank goodness. You typically need to use some sort of bisection search to find the smallest row, but that's fine. I mean, if you can solve one of these problems in a millisecond, then there's no problem solving 10 or 20 of them. And it turns out that a lifting dimension of 1 appears to find you the best possible row in every case that we've looked at, which is also kind of interesting. Now, I have more to say about this later, and it also depends on what sort of performance metric you're using. But for convergence rate, seems like this is pretty straightforward and at least a really simple LMIs. So just to give you an example, for smooth, strongly convex functions, if you give me the function parameters and the algorithm parameters, for example, the alpha and the beta for your algorithm, computing the tightest row takes about 50 milliseconds on my laptop. So, with that kind of speed, you could try thousands of different possible tunings really easily. This is what you get when you apply the approach. Now, I just want to draw your attention to the plot on the left. This is a plot of convergence rate, so smaller is better because my distance to optimality is scaling by a factor of rho at each time step. So rho equals 1 means I'm not converging, and then the smaller the rho, the better. And these different this is the condition ratio. This is L over M. You can think of that as how squished those quadratic contours were at the beginning. So higher means more difficult to optimize. And the black and the blue were the lines from before. So this is when we were just looking at quadratic functions. This is how well you can do with Nesterov, and this is heavy ball. Remember, heavy ball was the fastest one. The purple dashed line is the bound that Nesterov derived in his textbook using estimate sequences. So anybody that's read that knows that that's actually a pretty complicated and involved analytical method to find bounds. It involves recursively generated quadratic upper and lower bounds that eventually, once you let it converge, gives you a rate bound on the algorithm. And this is what you get. And what you get from using the Lyapunov approach is the sort of maroon line that is in between. So analyzing Nesterov's method gives you a tighter bound on the performance of that algorithm than Nesterov's approach to bounding it did. Now, one thing I want to point out is that if you plot this slightly differently, so over here, what I'm plotting instead is the iterations to convergence. So this idea that if I want to converge to within some ball epsilon, how many iterations do I have to do? If you look at it that way, you can see that actually all these different rates that you get, they all lead to parallel lines. So they only lead to a constant factor difference in the number of iterations I need to perform. So in that sense, Nesterov's bound isn't bad or incorrect. It gives the correct asymptotic scaling. It's just you can improve on the constant. Okay. But you can do a little bit more now that you have this more refined analysis. So I'll give you some examples. Nesterov's tuning uses these choices of alpha and beta. And I'm going to look at a slightly more general algorithm that looks like this, where you'll notice that now, instead of having the beta in here and here, I allow these two coefficients, two parameters to be different. So the sort of Polyak momentum term that tells you how much you adjust your update versus the interpolation term here that tells you where you evaluate your function are in general allowed to be different. So the first thing you can show using this approach, this more refined approach, is that actually this choice of beta and eta doesn't give you the best possible rate for Nesterov's method. You can actually get an improved rate by using a slightly more involved constant. Now you're still using the same alpha, but if you use this different beta and eta, you get a better rate. So that's the first thing. And you can do this with this more refined analysis. The second thing you can show is that actually if you allow beta and eta to be different, you can do even better still. And Professor Emmenbauer mentioned this as well, this idea that this triple momentum method developed by Van Scoy and others. And again, these are specific choices of alpha, beta, and eta that give you the fastest possible convergence rate, and it's faster than anything you can achieve by forcing beta and eta to be the same. Okay, but these results were all leveraged this dynamical systems perspective, right? We would not have been able to derive these new results if we didn't have this new way of looking at the problem. I want to tell you about, I'm going to now go into the next stage of the talk. I want to tell you about algorithm designs for noise robustness. And here we're going to see that this sort of excessive optimization of algorithms has a price. It doesn't come for free. Something else is going to happen once you try to optimize the rate too much. And we're going to talk about different trade-offs that can occur. So that's the next portion here. And just to illustrate what's going on, I'm going to start with a simple example again. Let's look at gradient descent. And here, remember alpha is the step size, but we're going to imagine that we have a noisy gradient. We're going to imagine that we have additive stochastic noise to the gradient. So we have access to this oracle g of x, but it's perturbed by noise. And we can still use an algorithm like gradient descent. In this case, it's called stochastic gradient descent. Let's see what happens. So here is a plot of convergence. This is the error, distance to optimality, and then this is the number of iterations. And here I'm using different step sizes. Now, what you're seeing here is what you might expect. This idea that if I'm far away from the optimal point, then the noise doesn't really matter. And then in that regime, then, well, I want the largest possible step size, right? I want to take the biggest possible step size as I can to guarantee convergence. But once I get close to the optimal point, then I converge to different sort of balls around the optimal point because the gradient is noisy. And because I'm amplifying that noise with my step size, smaller step sizes produce less amplification. So if I start on the optimal point, I really want to have no step size at all because I want to stay there. So you get this nice trade-off between the two. I'm just going to call these the sort of geometric phase and the stationary phase of my algorithm, right? And you can quantify this. Obviously, you want steeper is better, and you can quantify this as well. Of course, you want lower is better. You want to get closer. And for gradient descent, there's clearly a trade-off between the two, and it's very obvious how to trade those things off. It's obvious that the step size mediates that trade-off, right? It's obvious that if I take larger steps, then this is going to be better and this is going to be worse, and vice versa. So we can quantify the performance of the two phases for the geometric phase as rate of convergence, which is what we were talking about before. You want the distance to be scaling as some geometric function of rho here, and smaller rho is better. How do we quantify the stationary phase? Well, you can think of that as this expression here. You could think of it as sort of the long-term average over time of my distance to optimality. You can think of this as a steady state variance as well. And obviously I want that to be small as well. So I have rho and I have gamma, and these two things are, I'd like to trade them off. And so here's the question. Can we mediate this trade-off between speed and robustness for accelerated methods? You'd think that trade-off should still exist, right? But now it's not so clear anymore. If I had gradient descent and I said I want to make it more robust, then it's obvious what I do. I make the step size smaller. But if I have a momentum method like Nesterov's method or heavy ball, and I've decided I want to make it more robust, what do I do? I mean, I should probably make the step size smaller, but what about the momentum parameter? And what if I'm using one of these triple momentum methods that has more parameters? It's really not clear what to do anymore. So again, we're looking at this family of 3-parameter algorithms. And just to remind you, it subsumes gradient descent, Polayuk acceleration, and Nesterov acceleration, right? These things are all special cases. So this is the basic framework or idea of the analysis. We have our algorithm. It's characterized by these 3 parameters. We have the analysis tool. This is basically looking for Lyapunov function of quadratic plus function values. We also have the function class characterized by M and L. And we're going to be able to get 2 things out of this, a convergence rate and a sensitivity to noise. And then we can maybe close the loop here and do some design to decide what are the best algorithm parameters to make this trade-off happen. So for bounding rho, for figuring out rho, I'm just going to go through these 2 boxes now. Rho is exactly the same as what I talked about before when we were just analyzing convergence rate. This is the exact same idea. There's some sort of positivity condition and some sort of decrease condition you need to ensure. And if you have those 2 things, then you can guarantee that you have convergence rate rho. And how do you turn this into linear matrix inequalities? Well, then you add these combinations of valid inequalities to both sides. That's the basic idea. Okay. How do you do this for gamma? Well, it turns out you can also do something similar. You can write down a pair of conditions, one of them positivity and the other one a decrease condition. And you can do the exact same thing as before, add these valid inequalities to both of these. And then if both of these are true, then you can end up showing exactly what you wanted to show about your system. So it's very similar to the Lyapunov approach, but it's been sort of adapted for bounding gamma rather than rho. So both these methods lead to linear matrix inequalities. Both of them are really efficient. So what changes? The size still doesn't depend on D. It's still L equals 1 for the best rho. But now it turns out you need to make L a little bit larger. You need to lift a little higher in order to find the best possible gamma. Now, we're not sure what the best possible L is. We've tried increasing it more and more, and it seems like the results keep improving, but the improvements keep getting smaller and smaller. And once you get to somewhere between 4 and 6, now the improvements that you're seeing are sort of at the same level of the precision of the solver. So it's really not clear whether we're actually seeing improvement or not. But you get the best that you can get pretty close when you use something like L equals 4. Sometimes you could do 5 or 6 if you feel like it. But the point here is that even though this is a larger LMI, you no longer have to do bisection because your LMI is now linear in gamma, so you can just solve it in one shot. So it turns out both approaches, finding rho or finding gamma, both take about 50 milliseconds. So the total is about 100 milliseconds, and then you can get both rho and gamma. So what happens if you just try every possible algorithm? Seems like a reasonable thing to do. And each algorithm is a different point in this plot. So on the vertical axis, I have gamma, a normalized version of gamma. And on the horizontal axis, I have rho squared. So you can see this kind of looks like a trade-off. Seems like algorithms over here are unachievable. And algorithms over here, you could probably achieve them. Now, I've put a few other algorithms on the plot here. This is Nesterov's method with a standard tuning. This is the triple momentum method. Now, we know this is the one that should get the fastest possible rate, so it should be the leftmost point on this plot. And it appears to be the leftmost point. And then you've got this point. The Nesterov's method appears to be suboptimal. And there are points here that achieve either a better rate or better robustness or both. And then these points here are gradient descent with different tunings. The reason I drew a solid line connecting them is because as I change the step size, I get more robustness. And so this shows you the trade-off. But obviously, we do better if we use an accelerated method because we can be down here. So the question is, can we figure out what algorithm lives on this optimal boundary so that we can trade it off with a single parameter and say, this is how you tune your algorithm to make it more robust or faster? So let's talk about design a little bit. Now, there are some challenges to this. It's a linear matrix inequality, and as was pointed out before, it's a non-convex optimization problem. It's not easy to solve. But it is a semi-algebraic set, which means it's just a combination of polynomial inequalities. Now, in principle, I should be able to solve that because it's not that big. So you might say, well, why don't you just do that and get the exact answer? The problem is that if you do that, it leads to polynomials of very high degree that you have to solve. And at this point, the practical side of my brain says nobody's going to use an algorithm that requires finding the roots of a 200th order polynomial in order to get the parameters of your algorithm, right? That doesn't make any sense. Though I suppose you could do it offline. So the task is, can we find algorithms that have simple and explicit algebraic expressions, but that are close to being optimal? So maybe they're not exact solutions of this, but they're close enough. So we were able to do that. Just to give you a brief overview of how we did this, we basically used a numerical solver to find locally optimal points. So we did this numerically, but then we went back to the LMI and writing it as polynomial optimization problem, we went to look to see which of the constraints were active. So a semi-definite programming, you can think of that as the feasible set being just a combination of a whole bunch of polynomial inequalities. And you want to figure out where the solution lies on the boundary of that set. So if you figure out which constraints are active, then those polynomials are going to be of lower degree, and then you can solve those ones and hopefully get simpler answers. And also when that happens, the linear matrix inequality drops rank. So we used a combination of a sort of a numerically guided search combined with some algebra to verify our results. And this was the result that we came up with. So this is a single parameter algorithm. This is alpha, beta, and eta. And rho is the thing that you tune. And it appears in all three parameters. So it tells you how all three parameters, the step size and the two different momentum parameters, should be simultaneously changed if your goal is to trade off convergence rate and robustness to noise. And rho actually literally is the convergence rate of the algorithm. So that is the parameter you're using. If you use the smallest possible rho, this becomes triple momentum. And if you use a larger rho, well then, for that convergence rate, you're going to get the most robust possible algorithm. And it's near Pareto optimal. This was the same plot as before, and this is what happens when you plot the algorithm. So you see that as you can sort of pick where you want to be on this curve, and you get this nice trade-off between convergence rate and robustness to noise. This is for L of 10 and M of 1. You can also do this for L of 100 and M of 1, and you still get the boundary. And this holds true for even larger L and M. You'll notice that actually there aren't that many points here, right? It's quite sparse. And you might wonder, well, why didn't you just sample more densely? This is a very dense sampling. What you're not being shown here is that you see how this only goes to 0.12. Actually, the plot continues all the way up to 10. There are points in a very large space. I'm just looking at a small corner of it because when L over M gets really large, your chances of picking a good algorithm by random sampling are really low. So this is actually a very dense grid. It's just that algorithms that are close to being Pareto optimal are rare. So it's harder to find them by accident. Okay, you might be wondering, well, what if we used only Polyak or only Nesterov acceleration? Do we really need 3 parameters? And the answer is yes. The green region is what happens if you only optimize over the Nesterov family, and then the blue region is what happens when you only optimize over the Polyak family. So you can definitely reach more of the space if you use the 3 parameters. The next question is, what if I had 4 parameters or 5 parameters? Well, then the grid becomes a lot harder to do, so we have this sort of scaling issues. But we actually tried some preliminary numerical investigations, and we didn't find any improvement. We didn't find any way to improve on the 3-parameter family. So it's still an open question as to whether it can be improved or not for this problem. Okay, so I have 5 minutes left. I'm going to try to tell you quickly about distributed optimization. So distributed optimization is a problem that was alluded to before, but I'm going to be looking at it from a very different point of view here. The idea is you're trying to minimize the sum of functions, and you can think of this as a problem that combines consensus and optimization. Every different agent here has access to a different component function, so they can evaluate their local gradients, and they can perform gossip, which means just exchanging information with their neighbors. And the goal is for everybody to converge to the optimizer of the sum of the functions without ever sending all the functions to one person. So that's the goal. And you do this through gossip, and the idea behind a gossip step looks like this. So at each step, you multiply your current information with this gossip matrix, and this tells you how to weight the information of all your neighbors. And typically we assume, so that the sort of average is preserved, that these have row and column sums equal to 1, so-called doubly stochastic matrix. So there's a lot of different methods that people have proposed in the literature. It's almost like this cottage industry of let's come up with new algorithms and try to prove properties about them, right? And people have suggested all sorts of things with all sorts of really interesting names for them. And you see they all involve combinations of gossip steps. Sometimes you do 2 gossip steps. And then also gradient evaluations. There's a lot of different variants on this. And this is only just a sampling. There are many more. And in fact, I think I stopped looking at the literature in 2019. But it continues. Now, the point that I want to make, because I only have a few minutes here, is that you can still view this in the same framework, except that now you're feeding back 2 things. You're feeding back your gossip matrix and the gradient. And now your algorithm is, again, some dynamical system, but now you have 2 inputs and 2 outputs because you have the V and the U and the Z and the Y. And again, you just have some set of matrices. All these algorithms that I show you on previous slide all have representations in this form. So we should be able to analyze all of them in a common framework. And it shouldn't matter that they all have different names, right? You just plug in the different parameters. Okay, so we make assumptions on the functions here. We're going to assume the functions have a 1-point convexity, so it's a slightly weaker assumption than strong convexity. And we're going to assume that the gossip matrices are balanced, doubly stochastic, and have a spectral gap that's bounded by this sigma. So you could think of sigma as a single parameter that tells you something about how connected the graph is. So when sigma is 0, your graph is fully connected, and it should behave like a centralized optimization algorithm. When sigma is 0, your graph is disconnected, and these are examples, intermediate examples. Sorry, when sigma is 1, the graph is disconnected, sorry. So obviously, the smaller sigma is, then the more connectivity you have. This is the solution. The solution is, if you use this LMI approach as we did before, then there's 2 things you need to certify. You need to certify convergence of the mean to the optimal value, and you need to certify that everybody converges to one another. So you have sort of consensus and optimization, 2 things, and the result is 2 LMIs that are coupled. But their approach is basically the same, and you can see it's parameterized by the parameters of the algorithm, and also by M and L and sigma. And so if this linear matrix inequality is feasible, then you have convergence at rate rho. We didn't do the noise analysis for this one, but in principle you could. It wouldn't be any different. This is what you get when you compare all these different algorithms. Now, just to walk you through this, the different lines correspond to different algorithms from the ones I showed you before. On the x-axis, you have the spectral gap. So remember, 0 is completely connected and 1 is completely disconnected. And here I fixed L and M. I fixed the ratio to be 10. So L is 10 and M is 1. Now, there's these 2 dashed lines here. The dashed line over here is what happens when you're just doing pure consensus. So you imagine that there isn't any optimization you need to do. There's some limit to how fast people can all come to consensus by only using gossip steps. And this is that bound. So you're never going to be able to beat that. This is how well you do assuming a completely connected graph using gradient descent with the optimal step size. You can't do better than that either because we're using this one-point convexity, and in general, with one-point convexity, gradient descent is the best you can do. So we have these two lower bounds, and you can see some of the algorithms meet one of the bounds, but sometimes one algorithm is better and other times another one is better, so it's really not clear what you can do. I think that's my cue. I should be done soon. Okay, I'm almost done. Okay, so again, as before, the analysis is easy, but the design is still hard. It's again non-convex. But we can look for simple algorithms, as we did before. This is the algorithm we came up with. And this algorithm turns out to be very simple. It also has a nice interpretation. And we have closed form expressions for alpha, beta, gamma, and delta, the parameters of this thing. So this was the picture we had before, and this is what happens when you use the algorithm. So again, it can be no worse. It can be no worse than any of these other methods because guess what? We picked a parameterization that subsumes all those other ones. So of course it can only be better. But then the question of how much better can it be is still open. But this is the best that we could do in this setting. So we think that it's impossible to get to here, but we don't have a proof of that. By the way, there's a simple interpretation for this algorithm. If you're familiar with ADMM, the alternating direction method of multipliers, this is how ADMM would be used to solve this problem. Use an argmin on your local function, and then you find the average of everybody's states, and you make that your new state, and then you do this update. That's what ADMM would look like. The thing is, first of all, we can't do an argmin. I mean, that's like solving the optimization problem. We're not allowed to do that. And also, we can't do a full average of everybody's steps. So if instead you replace each of these things by reasonable proxies, so you replace this argmin by a single gradient step, and you replace this averaging with a single gossip step, you recover exactly the algorithm that we derived. So you can think of our algorithm as inexact ADMM. Okay, so just to summarize, iterative algorithms are dynamical systems. You can perform their analysis rapidly and automatically by solving small semi-definite programs. I showed you several examples. You can interpret these certificates very simply, just as Lyapunov certificates or dissipation inequalities. And I showed you examples of near Pareto optimal algorithm designs for rate robustness trade-off and an optimal or well, we think it's optimal design for distributed optimization. That's all I have, and just I also want to point you to the robustness trade-off paper is on arXiv. The distributed optimization paper is in TCNS, and any of these papers are available on my website. Thank you for your attention.
I think a lot of people guess what I'm going to ask. Just with I love those plots with the noise balancing variance and rho. But of course, those who know me are going to say have a vanishing gain algorithm. But so I know you can't do that. The method
what? Sorry, I missed
get a vanishing gain algorithm.
Okay.
I mean, the point of a vanishing gain algorithm is that it's big initially, so you get the fast geometric phase, and it gets smaller, so you get the variance stage. But maybe you can adapt your methods to deal with it. So, maybe you could have two alphas, and some detection method on when you switch from your geometric phase to the... Or
what you could do is you could take that trade-off parameter rho and change it over time.
Yeah, okay.
So actually, I have a slide for that.
Oh, cool.
I can show you. We tried that. Hold on. So we tried doing that. Yeah. So this is an example of one of the algorithms we designed. It's robust heavy bulb. This is for one of the cases, but this is basically what the idea is that it's parameterized by rho, and different versions of the algorithm give you different versions of this trade-off, right? This is when you pick a really aggressive one where you converge quickly, but then you converge to a ball. And then you can pick the slower ones where you converge more slowly at first, but then to a smaller ball. And then the red version is what happens when you start with the large rho, and then at each time there's a dot here, you switch to a smaller rho. Yeah. Or sorry, a larger rho. Yeah. So it is possible, though the one thing that's tricky about our analysis is that it's important that the switches be discrete, at least for the way we design the algorithm, because we can only prove convergence for constant rho. Right. So if you were to continually change rho, I can't guarantee that the transients won't eat you.
Yeah.
Because the changing of rho, you're actually changing the dynamics.
But so I think two-time scale stochastic approximation would answer the question. I think you actually could.
Well, that's basically that's basically
what
this is.
Because the log scale is...
Yeah. So, yeah, exactly. Yeah.
Okay,
and
cool.
these two are the two optimal bounds, right? This is the bound you get from. This is the best you can do for estimating, the mean of a random variable, right? Central limit theorem, I guess. And then this is the best rate that you can get based on Nesterov's lower bound. So you actually can meet both lower bounds this way.
Cool. Great talk.
Thank you.
So I have a question regarding the distributed algorithm. I was wondering, do you have a method to select step sizes that can be done in a decentralized way? Or you need to solve a system-wide LMI in order to find the step sizes that work?
So the version of the problem that we solved has everybody running the same algorithm. So is your question, can we run some sort of consensus so that everybody agrees on what algorithm to be running, or?
It's
Sorry.
It's all right. It's how to select the step sizes that guarantee convergence of the algorithm. Can it be done in a uncoordinated fashion, or you need to run the LMI like in the centralized method?
If you think about what we needed in order to figure that out, we're looking at being robust with respect to the graph. So the only thing you need to know is M and L and sigma for the graph, and that's it. Everybody, if everybody has access to that information, then everybody can compute those step sizes. If the setting is more complicated, like if each agent has a different L and M, then the problem becomes more complicated. And I think you can still formulate it as a linear matrix inequality, but I suspect then it would scale with the size of the graph. We also wrote a paper several years ago where we solved a similar version of the problem where we assumed that the graph is known in advance. That version does scale with the number of nodes, but it gives you a more refined algorithm that is graph dependent. So it allows you to find different algorithms for different graphs. The version I showed you here is a version that is graph independent, where you just summarize the entire graph with just one number, sigma, which is this proxy for connectivity. But yeah, I think there's a lot of different things that are possible.
Last one.
Do you mind making the slides available online?
I don't mind.
Okay, that's all I had to ask. Thank you. I'll send an email about this.
Yep.
We have one more, so I'll steal and ask one myself, actually, if no one minds.
Yep.
So with this, right, when you have a changing step size, you're effectively looking at something that's non-autonomous, right, or a system where like the basically the A, B, C matrices change with time, right?
Yeah.
Is there any fundamental reason why that's challenging, or just haven't looked at it yet? Or do you think it could be possible to design diminishing step size algorithms by looking at non-autonomous systems?
The reason why it's fundamentally difficult is that if you're going to find a Lyapunov function, well then it's going to have to be a time-varying Lyapunov function for your time-varying algorithm. Or you can try to find a more complicated Lyapunov function that is not time-varying, but that works in spite of the variation. Yeah. So a sort of robust Lyapunov function. Both of those things are difficult. As far as I know, nobody's tried the latter, but the former we have done. There is a version of Nesterov's method that involves parameters that change over time. Yeah. It also gets the same worst-case rates. It's just a different way of running the algorithm. We were able to analyze that one in the convex but not strongly convex case, or sorry, basically strongly convex but with m equals 0.
Yeah. Yeah.
And in that case, what you get is you can get this like time-varying Lyapunov function, and you can show that you get the 1 over k squared rate. So you can derive all these results. The only thing that isn't very nice about it is that it isn't as automatic. I mean, we had to sort of work really hard to find the Lyapunov function, and you could look at our analysis, and it would be fair to argue that it was not an automated method. We sort of had to tailor our analysis to the algorithm. So that's why I don't like talking about it so much, because I don't think it's a very elegant extension to what we have so far. But I would be really interested in finding other ways to tackle that problem, ways that are more systematic. Yeah.
Cool. Thank you. Okay, we'll have to move on. So let's thank our speaker again, and